see how fast that one goes? See, this one is slower. So this is showing exactly, if you're in the equator, it goes 465 meters per second. Well, when you're here, it's almost none. So what was the photo did? He was here, it's almost like Denver, almost like Denver. But I know there is one in the South Pole, but it's only for scientists. If I had a pendulum here, it is going to be independent. It's not going to do anything. It can swing back and forth. The reason why we have here, like I'll show you in a minute, because of deflection, because of Coriolis effect. See, the easiest way to understand is just because we're talking about planets. You have all seen merry-go-round. There are two kids sitting on a merry-go-round. I'm throwing balls, and then he or she is throwing balls to me. We can catch easy. But see, what happened, that merry-go-round is going with the Earth. They don't feel it. But as soon as I turn on the switch, and then she's throwing the ball to me, I miss the ball. That's exactly Coriolis effect. So in a merry-go-round, it's a smaller scale, you can see it. We're going to demonstrate exactly. The Earth is like a merry-go-round. It doesn't make any difference. But the only difference is merry-go-round is flat, Earth is round. It doesn't matter. But the concept is exactly the same. So if I throw the ball up the green, you won't be able to catch because it's accelerating frame of reference. It doesn't matter clockwise or counterclockwise. So you see how easy it is to get the concept, how it works. So the on equator always you go warm, and then if I have a pendulum here, guess what? There won't be any deflection whatsoever. There won't be any. English people, you know how smart they are. It was World War II, and then we're talking about 60 years ago in Falkland, in the southern hemisphere, and they had never fought in the southern hemisphere. They were throwing shells to Argentina, and they had no idea. Instead of hitting the target, it was not only the target, but almost, like 6 centimeters away. And then they realized Coriolis effect on this hemisphere is exactly opposite. If I take this pendulum on the, Brazil or, places like Peru, it's going to go the different way. Here it's going to go clockwise. In Peru, it's going to go counterclockwise. So the English people had no idea, and then after the war was over, they realized they fought in northern hemisphere. Coriolis effect is to the right. In the southern hemisphere, to the left. And then they corrected that. So even though they knew the concept, but they have never ever experienced. So now I'm going to demonstrate this. So instead of sand, what I did, you can come close sand if you want. So what Mr. Foucault did, he had sand on the floor, and I think he had a lot of friction, but that's okay. So instead of sand, what I did, I used this 6x6, and then this is called plane. So you can see why I release this. Now I have gravitational potential energy. When it's get to the center, it's exactly toward the center of the Earth. But when it goes away, it has kinetic energy. It's going to go back and forth, back and forth. But the killer in this place is what? The air resistance. You can see I have a friction over there where the bumper is on, but that is nothing. But this is pushing air, like the one I showed you, is pushing air aside. So no matter what, if I let this go, the second swing or arc is not going to go exactly like the first one. It's impossible. So what I want you to guys know, so when I release this, after a few seconds, we are all accelerating with the Earth, but this is not. Why this is going back and forth? So Earth is going underneath. So in other words, now we are going toward the east, right? So look. Oops. Oh, sorry, I should go the other side. See how far. But look, after a few seconds, you can tell it's not exactly aligned with the line. You see? Did you see that? Now it's going like 5 degrees. So why this is going back and forth, where it is going underneath. But there is an always important concept. It depends on your latitude. So latitude means horizontal, longitude means vertical. Well, in England they call it British. That is the frame of reference. That frame of reference, they call it AM or PM, all of you know. So all this communication, satellite, and everything else has to do with the longitude and latitude. Now here, we're exactly like Paris. So no matter what, this is going to be deflected. Do you see what happened? In a few seconds, you get like 15 degrees. Can you folks see it?
Yeah.
Dr. Greg, can you see it?
I can. If I can just jump in and use some words that we used last semester. So the Bob feels a fictitious force because we're in a non-inertial reference frame.
Exactly.
It feels a fictitious force pushing it around clockwise. Because we're in a rotating reference frame on the rotating Earth.
But folks, I have to clarify something. What Mr. Foucault did, it was a huge place. Like I said, his period, mine is only 2 seconds back and forth, but his was 16 seconds. And imagine that 28 kilograms and 220, and every time 16 seconds, the Earth rotates almost like 150 kilometers underneath. But ours is so small. But it doesn't matter. It shows you exactly how it works. It's the same thing. Mine was maximum 140 degrees. The reason why it runs out of energy. Back and forth, See what happened now? We got almost 30 degrees. And then, if you guys pay attention here, something important is happening. You see, it's not going in the same line. Did you see that? The sharp ovals. Did you see that? See, it's going this way, that way. Because this ceiling is going with the Earth. Floor is going with the Earth, but this bob is not. That's why it's accelerating. And technically, the physicists always say that, the force, Coriolis force, is a direct consequences of inertia. So this bob is resisting acceleration. That is so important. It's a direct consequence of inertia. Inertia can be for the planet, can be for everything. It's resisting acceleration. So Dr. Gray, I was wondering, shall we wait or just because he's showing the concept. Now, after a few seconds, it's going to go like 90 degrees. And like I said, maximum it goes 160 degrees and then it stops. The reason why? Because of air friction.
Right.
If we do this more, it's going to go forever.
Well, I think
so
we should move on.
Okay. Okay, folks, if you have any question, please after because unfortunately we have only 1 hour. So after the class, I'll be happy to stay even outside because Dr. Gray is so busy. And then I can stay as long as you want because some of these concepts are complicated, I know. So I can explain to the best of my knowledge. Okay. So the second one is so important. I saw this in Caltech because I had a physicist when I was graduating in Los Angeles. And as a matter of fact, Caltech in the United States or in the world, I would say, when it comes to physics, is the best. And guess what? CU Boulder is 15 in the rank. Can you believe? That huge university which is doing a lot of science projects is 15. Caltech is the best. Folks, this is index of refraction. Our perception might change. And especially when we have a oil like this, it's a cooking oil. You can see the magnification on this one, but if you look through this, you won't be able, well, of course you have to look in an angle. You won't be able to see the So index of refraction is the measure of how much light is bent. Bending is not a good word, but technically they call it refraction. See, light so fast in vacuum, but we don't have a vacuum here. In air, it's different, but as soon as it is in the water, it has to change the speed. That's why we are perceiving that, when you have a spoon in like a tea, you can tell it's broken. So this is exactly the way it works, and this is the oil. If you look through the angle, you won't be able to see the Pyrex. The reason why, not from here, you have to have this angle, exactly. The reason why light travels from our eyes, glass, into the oil, and because they have exactly the same index of refraction. So in other words, oil, cooking oil, and the Pyrex are exactly the same. We cannot perceive whether the light is coming or going, but here we can tell. You see how magnified it is? If I move this closer, can you see, folks, in the water? You see the magnification? It's false, but you can see the magnification. If I come closer, what happened is less magnification. Did you see that? Can anyone tell me what's happening? Why do we have less magnification? So can you tell me why? When I'm going closer.
Well, moving closer with the angle of the light coming in, there's change.
Angle is good, but there's an important thing here. See, light is not traveling. The distance is important. If I get this close to this wall, there won't be any magnification. The reason why light travels from your eyes through the glass, through the Pyrex immediately. But here, what you have in between is a different, is water. Light does not travel the same way. You see? The distance is important. So, well, of course, you can tell, I'll give you one. You're standing over here in the pool. Fish is right there. You can see exactly where the fish is. But when you have an angle like this, you don't see actually where the fish is. The actual fraction. Because see, if you have a perpendicular here, exactly like this, that is your perpendicular. The fish is here, but you don't see the actual position of the fish. You see it over here. So this concept is so important, and the human's life are saved on this, because the same concept is used for fiber optics. Remember when I was like a student like you guys, I used to have a doctor, and he would take me to surgery because I was not afraid of gloves and things like that. And then he was showing me exactly endoscopy. You would go inside the stomach, you would get samples, you would even, put stitches in the stomach. But the point is, in the stomach you won't be able to see. Fiber optic is using the same concept, but how? It's exactly like a wire, but what happened? The core has more index of refraction. The light goes in, it's trapped, won't come out, and the cladding has less. So it doesn't matter how you bend that, the light is going to go through. See, the reason why we can see through, if there's a tunnel, we can see through all the way. What if that tunnel has a curve? Won't be able to see it because light won't go through. So I have seen that how important the fiber optic is, and Dr. Gray knows. Some people even can get PhD in fiber optics. Really, they can.
Yeah. Did you all talk in lab about total internal reflection? Are those words that are familiar? Okay, so fiber optics use that principle.
Fiber optics, yeah. Well, as endoscopy, well, of course, like I said, unfortunately, due to lack of time, because this concept is so important, how you see things are different. Your perception is always not exactly the way you see things. Now, I see sun in the sky. That's not the actual position. Can anyone tell me why? The sun sets, right? Is that the actual position of the sun? Why? Why do you have exactly atmosphere? See, it's not dense like water, but you can see the old days, people would think, well, they'll find water in a railroad track. They go and go, they never find that water because light strands. When you see the moon, that's exactly not the way it is. That's not the actual place. Because the only way you can see is the Hubble telescope. But of course it's not for us, it's for scientists. Because Hubble telescope is illuminating that atmosphere. They take the best pictures of universe, all the galaxies and everything else. Hey Dr. Gill, what was the third one I was wondering?
Second law of thermodynamics with spring.
Okay. Yeah. Folks, I did explain that this is where the spring is. Sorry folks, we're a little bit unorganized here because it took us for a long time to see where the springs are.
Let's see. Are these your Hooke's Law springs with big springs and these springs?
Oh, right there. Okay.
These springs. Okay.
Folks, this is a simple thing. Albert Hooke was a great scientist, and I don't know how true it is. They said that Isaac Newton got some ideas from the Hooke. And the Hooke is so famous for the spring. And it's amazing, this spring is used in technology a lot. You push on it, it's pushing back. So what I did, I compared with the Earth. The reason why you have now feeling your weight, because Earth is pushing on you. You may not feel it, but amazingly, it's proportional to your weight. If I weigh 200 pounds, Earth is pushing me 200 pounds. If I weigh 150, and it's amazing, the deflection is proportional to the force. I get more force, more deflection. But it has to go back to the state of equilibrium. It doesn't matter how much you push. See, as long as you don't damage the spring, it has to go back. But there's important thing, and I don't know why the scientists never explain this. See, when I push this back and forth, what will happen? Thermodynamics comes in equation. So what happened? This is getting hot. But unfortunately, what happened? I lost that thing. I had a glass thing made on this. And then I had thermometer, which is non-contact. So in other words, you can feel it without the thing. When it goes back and forth like this, you never feel the heat. But that heat is the entropy. So in other words, it's a disorder. So that shows exactly is the entropy. But unfortunately, I don't have it. But I want to show you, anytime you have any motion, no matter what, the second law automatically comes in equation. That's why the universe, like I explained before, everything works with the second law. You have electricity. You hook it up to your